So let's have some slides. So the work we do, you can summarize under the notion of living machines. So we think about ourselves as living machines, but of course you can take this metaphorically as de la métrie or so, but you can also take it as the idea that human minds and human bodies and any biological system is based on principles that are identifiable and also principles that we can synthesize. And in this synthesis, this is another relevant point for me, in that synthesis of living machines, we actually validate our theories, right? So I have no confidence whatsoever that physics will solve life, or that physics will help us explain consciousness or mind. This takes very different methodologies. And in some sense, the massive influx of physicists into neuroscience with the little impact they've had over the last decades, or neuroscience in general, is sort of illustrating that point, right? We should not naively believe that if we can generalize from a scientific discipline that's been very successful dealing with dead matter, that this will just work on living matter. Okay, so as far as I'm concerned, we need a new paradigm, a new way of thinking, a way of testing our theories, and it is largely grounded in this idea of building, if you want, artificial brains and artificial minds. So the work that I describe is done with many people, with my group SPECS in Barcelona. I'm hosted by the Bioengineering Institute of Catalunya, and I'm actually paid by the Catalan Institute of Advanced Studies. So this is a group of people with very different backgrounds, from engineering, math, physics, to the life sciences, to the humanities. And I really feel it's this sort of very multidisciplinary team effort that's required to have an impact in this area. Okay? And it's largely supported by European money. So, as you know, there are people, especially here in Silicon Valley, there are quite some fans of this project, who pour quite some resource into searching the heavens for extraterrestrial life. And so far we still haven't succeeded, so maybe we're out here on our own, or the Fermi paradox. But Frank Drake summarized that the search and the problem we're trying to solve in his well-known Drake equation, where you basically just try to list in a more systematic way what are the basic preconditions that must be satisfied for life to emerge on any planet, right? Of course, these are obvious things. There's sort of astrophysical components and biological components. Then there are, if you want, cultural aspects to technological aspects. But he also added his famous parameter L, which basically is a parameter that says how long a civilization will exist before it disappears or destroys itself. Okay? And that actually then raises this fundamental question: what's the L of humanity? Right? What's our survivability? Because for some interesting reason, we just assume it's open-ended, right? Even though we're surrounded with a lot of evidence that would tell us that maybe it's not. So, right now, for the first time in our existence, we actually are confronted with this question: what's our survivability? How many years do we got left? And this is a fundamental aspect of the Anthropocene, right? So right now we live in an era where humans, as such, are a dominant geological force. We are now, and also some of our speakers already highlighted that, but what this highlights, if we agree we live in the Anthropocene, it also means that we are the problem, right? We are the cause of these major changes that we can observe, and we are the cause, or we are defining L right now. It's not a meteorite. That's just a distraction. It's us, right? So, and that, of course, raises this fundamental question, okay, how can we identify and overcome any kind of liabilities and risks that are associated with being human? And there are many. So today, 75 years ago, that the Allied forces landed in France. They then fought their way, in the end, into the German heartland, where, together with the Russians, they beat Germany into, if you want, surrender. And this also shows you a little bit what humans are capable of, and also how much suffering people had to go through actually to try to readjust or overcome these challenges we pose to each other, because this was also a human-created problem or disaster, right? So that means maybe we should point our telescopes on this alien technology, our brain. This is our big challenge. Meteorites, aliens are distractions. This defines L. If we care about our future, the future of our descendants, this is what we should worry about. Right? Not only out of scientific interest anymore, but because it becomes critical for our survival, because we are also dominating the forces that shape evolution. So let's look at the brain. This is a representation of the human brain that we built with our system called BrainCube. You can download the free version on this website, brainx3.com. And so what we're trying here, you can look at some of the connections in the human brain that are revealed with diffusion tensor imaging. So you can basically look at the distribution of water in the brain and from that determine what are the main fiber bundles, and you can visualize them. Here we look at some of the subcortical structures like the amygdala, the hippocampus, the basal ganglia, the outside shell here is the cortex. It's about 90 billion neurons, all densely interconnected. And actually, it's not like the internet at all. So the real question is, however, how do we link this bit of matter to its functional properties or psyche, right? In the end, when we pose questions about understanding the brain, the operational questions are not really about how many receptors you can fit on a dendrite. It's actually how these structures support core functions of this brain, like memory, attention, learning, perception, consciousness, so on. These are all questions that traditionally are in the realm of psychology. So if we want to pose that question, what it is to be human, the brain should give us information on that. And we are on a trajectory now where we have turned ourselves, at least conceptually, the way science is looking at us being human, at least the neurosciences, we are not that far removed from billiard balls that are governed by external forces, as this billiard ball would be governed by the laws of mechanics. So starting with the early 20th century behaviorism, and here we have one of its main proponents, Skinner, it has turned us into zombies, right? Zombies driven by external forces. And actually, if you analyze this in more detail, how we went from the mid-19th century from studying consciousness as the core question in psychology to where we are today, which is actually a very largely big data-driven black box view on brains operate, it is devoid of meaning, right? So we have really sculpted out all the content from this system to turn it into this zombie billiard ball, okay? This has been gone via the steps of behaviorism, cognitivism, or the computer metaphor, if you want, and then the last decades are very much dominated by a more metaphorical utilization of biology. As now we speak of neural networks doing things that have nothing to do with neurons. It's just metaphor, it's metaphor, okay? So this is how we have squandered meaning by relying on metaphor. People speak of artificial life. The systems they build have nothing to do with life. So let's just be clear about this, okay? These are algorithms that do things that in someone's imagination would reflect some property of life. Okay, so we should be much clearer what it means to then speak about the brain. Now the brain, as you will all agree, so here we look at the evolution of life forms on this planet. The brain is a product of evolution. And this is not a big revelation. But what's interesting, if you look at this, the distribution of life forms over time, that we have this very short period, about 560 million years ago, of the Cambrian explosion, where the amount of life forms on this planet emerged, increased very rapidly in about 50 million years. Actually, in this very short period of time, all body plans we know today were invented. Okay? Together with these body plans, also the brains that had to control them were invented. So that would mean that in this period, if you want, the seed was laid that defined the basic design principles of the brains that we also know today. So that would mean that we have to place our thoughts and our investigation on the brain, including the human brain, in this evolutionary context. Right? So what then is the function of this brain? Well, we can converse with Claude Bernard and Ivan Pavlov, who both actually saw the brain as a device to mediate between an organism and its environment. Right? They had a sort of an intuition of homeostasis, even though they didn't use this word. This came in the 30s from Canon, but it was a system that would help the organism to find some sort of balance in its relationship with its environment. But that would imply that already for these grades of the study of living systems and dynamical systems, in the end, brains are all about generating action. And this is not a trivial or irrelevant statement, because if you now say brains are about generating action, it also means you commit yourself to understanding the brain as a control system. That means questions around computation or questions around information are not that relevant anymore, or are now phrased within a broader context of control. And I think this is an important shift. So what does it mean to control action? Well, in my opinion, all you need to do is to optimize 4 functions to take care of your interaction with the physical world, right? So in order to answer this question of the how of action, what should I do now? We first have to identify what is the goal that drives action. What's the need that must be satisfied? Then what are the objects in the world that speak to those needs, the objects of my desire? And then what's the spatial configuration now of the situation I find myself in relative to these objects? And lastly, the only thing you then have to optimize to worry about is time. That is, how do I adjust my dynamics, my conformation, the shape I take, to the actual dynamics of the task I'm trying to realize? So we have developed a theory that is looking at how you can optimize these 4 objectives of the brain engaging the physical world in generating action, called distributed adaptive control. I just want to give you a bit of basics, because in this framework we're going to look at some specific questions, okay? So basically, DEC just says, look, the brain is a layered control structure, and it starts with the body itself. So it incorporates all these ideas that come, for instance, from Rolf Pfeiffer. Actually, I worked very closely with Rolf Pfeiffer in the early 90s. The body itself is the first layer of control, right? That's where the morphological computation aspects would come in, where you have the sensory sheets, the needs, the physical needs of the system, and its effector systems, its skeletal muscle systems, right, in our case. But on top of that, we have a layer of reactive control, which is strictly predefined and mapping sensory states into stereotyped behaviors via drive states, as in reflex control, right? So a whole bunch of very primitive reflexes, which actually can turn out to be pretty complicated stereotyped behaviors, and this control layer runs on top of this somatic layer. But now we have a big problem to solve, which we already know from symbolic AI, which is called the symbol grounding problem. But since we now live in the day and age of amnesic science, people are still just predefining all the knowledge in their systems, believing that that gives them any sense of autonomy, which is not true. Already then we knew that you have to think very deeply about where the meaning comes from of these representations that you predefine. And then in the DEC control structure, that's done by the adaptive layer. We're saying, on top of all these reactive control systems, I have learning and memory systems that are classifying the world, that are classifying my action states, and they do that, they link the two through value systems, if you want, through emotional systems. I'm thrown in the world, I don't know anything about tables and chairs and so on, I'm going to figure that out. That's what my adaptive layer does. It learns me to classify my state space with respect to the world and myself. Okay? So once I build this state space, I can start to think about strategies or policies for action. Right? So now I'm going to rely on different kinds of memory systems that allow me to put these states together over time, so I know how to get from here back to the parking lot to get my car. It's a sequence of states of the world and of myself. And they're strung together relative to a goal. Right? So this is now how I can start to build my policies in a fully bootstrapped fashion. And then on this architecture, you can map these 4 objective functions you got to solve. And also we've already shown that all these popular neural net models people build, or Q-learning models and what have you, are all subsumed within this architecture. But they're just small slivers of the whole story. And that's why these models themselves are still incomplete and are not going to scale. So this is a bit a theory, right? But how do you test such a theory? So here we got the brain again. And how I'm looking now at this brain is, okay, let's now see what are the generic design principles across all these brains, right? As we looked at earlier. And in that sense, we should be also inclusive. We can also include, to at least consider, the linking between invertebrate brains and vertebrate mammalian brains. So this is a really nice paper by Nick Strausfeld and Frank Hurt, who also showed that at an anatomical and genetic level, we can find homologies between insect brains and mammalian brains. This doesn't mean it's immediately true, but it's an interesting questioning about what are then these underlying principles of brains. Were all brains that ever existed based on the same small subset of principles? That's at least our starting point. Okay? And then the DEC architecture tries to capture those principles. So if you map this to the brain, it looks like this. So here we have the reactive control layer, your reflexes, which in a first instance you can map to essentially states of the world, which will be your superior colliculus. This is in blue. Then we have the states of self, which would be your hypothalamus, which is here marked in red. And action states would be here the central gray area, which runs essentially like a little tube along the fourth ventricle. So why is that? Well, the superior colliculus, or the tectum in simpler organisms, is a sensory system. It detects states of the world, right? The central gray area has an encoding of pretty complicated stereotype behaviors. If you stimulate, you can trigger defensive behaviors, aggressive behaviors, sexual behaviors, right? Stereotype patterns, they're all in there, pre-coded. While the self, it will be encoded by the hypothalamus, which is really sensing states of the self, right? So you can map this idea of world self action directly to these specific brain structures. But for the adaptive layer, what we're thinking about here in particular is again more the medial temporal lobe, like the hippocampus, and the temporal lobe as sort of the top end of a whole classification hierarchy of states of the world. I will talk a lot more about the hippocampus later, but that's really seen as the core system underlying our ability to form episodic memories, right? Like you remembering tomorrow you were sitting in this room and you were listening to this talk and it didn't make any sense to you. Okay, that's an episodic memory that you will have tomorrow. In green, we can look here at the cerebellum, which is about 70% of your neural hardware lives in the cerebellum. It is strongly linked to the control of action. Right? While the amygdala here in red and the nucleus accumbens here in red are structures that deal with the immediate processing of value. Right? So you see that this separation of world, self, and action can be mapped rather directly again to structures a bit higher up in the brain. Cerebellum, temporal lobe, and amygdala and nucleus accumbens. Well, if we now look at the contextual control, we will look at how do I form policies, how do I form strategies, how do I acquire cognitive control over the things I do. Again, we can find a relatively clean mapping from the supplementary and premotor areas, being strongly linked to the control of action. The orbital frontal cortex, being strongly linked to states of self, together with the insula, so sitting very deep inside the cortical lobes. And then in blue, more the prefrontal cortex, which you can see as your working memory of the states that this decision-making machine is operating on, states of the world and states of self. This is the state space on which it makes its decisions. Right? So just to show you that this framework, we are really pushing that towards understanding how different brain systems work, and it gives us also a little bit of structure in which we can look at brain complexity. And of course, I took several shortcuts. There are many additional complications, but at least we can start to see a little bit the forest from the trees. But what's also important from a more theoretical perspective, if you move up such a hierarchy, what you start to see, a brain starts to virtualize. Working memory systems that inform decision-making are operating on representations of states. This is not anymore strictly the physical world. It is a highly interpreted version of that. So you see virtualization as you go up, but virtualization, of course, gives you flexibility. It allows you to learn, but it becomes sequential. On the other hand, if you rely on these predefined, very simple brainstem systems, they are quick, they're based on predefined parameters or priors, but they're very rigid. You have no flexibility. And this is roughly the trade-off that you try to deal with, right? So an architectural perspective allows you to think about the brain as being a solution to a number of trade-offs. And this is often forgotten, right? We might think, oh, I want to understand vision. And then people just go for vision as it's sort of an isolated module in the brain, and forgetting that also vision is trading off, has to make compromises relative to other operations brain must realize, including just the metabolism to maintain all the neurons that implement these things, right? So the perspective that the architecture gives you is one of the optimization of trade-offs, in the end, through the constraints that deconstrain, right, which comes from Kircher and Gerhardt. So the questions about the brain that we should really worry about are these constraints, the commitments the brain is making to structural features that deconstrain its function. Right? A priori, I don't know what the content of my working memory can or will be. It will depend on the world in which I am situated. However, I have the ability to maintain these memories with certain capacity limitations. This is now a constraint I've committed myself to, right? So what are these constraints that we should think about? Well, there's a nice paper by David Van Essen and Henry Kennedy where they try to identify, let's say, the core processing structure of the neocortex. It's just an illustration of this idea of a bow tie structure, right, where you have constraints that deconstrain. But one concrete example of constraints that deconstrain are, for instance, neuromodulatory systems. The noradrenaline system, serotonin, dopamine, acetylcholine. If you're a smoker, you know a lot about your acetylcholine system. Dopamine, as an example, also interpreted as the reward system, allows you to learn in an open-ended way about any task, right? So it helps you, to the sense of Alan Newell, develop general intelligence, which is a system for which anything can become a task, right? So this is a constraint now that deconstrains. Now you can learn any task, but you can also get Parkinson's disease. That's the price you pay for that constraint, okay? So with that in mind, so what we're looking for in our study of the brain is what are now the constraints? What are the commitments the brain is making in order to be deconstrained, right? And then what are the boundaries of this deconstraining? It's not necessarily open-ended, right? So we have a theory, which might all be wrong, but it's a way to help us to pose the questions, right? And then we have the real brain. So how can we bring those together? Well, you know, to have a theory is one thing, but a theory is more than words, right? Theories have to do three things. You must explain something, right? You must make testable predictions, and you must be able to control something. You know, running an experiment is like controlling the universe, right? So any theory that's not able to do that is not worth listening to. That's just an opinion, okay? But we have to commit ourselves to explaining things, make it testable, and control stuff. So that's what we've been trying to do. So one thing we did is we built our own telescope here in Neuchâtel in Switzerland in 2002. This was an interactive space or a sentient space, and H.R. Giger was one of our collaborators. Unfortunately, he passed away a few years ago. He was also the creator of Alien. You might know Alien. Well, he was the artist behind it. But so the ADA exhibition, the concept that we were pursuing here was, okay, let's build a robot that's just a space, and that communicates with its audience through some abstract language of sound and light. Okay. So we built this thing, which was an enormous amount of work. It was running for 6 months. It was seen by over 500,000 people, which of course gave us a lot of data on how humans interact with these kinds of multimodal interactive systems. Like Ada now just woke up, and people can start to explore it. Okay? So we had enormous amounts of data, which helped us understand how do humans behave in such a space. Okay? And one thing that we observed here, you could distributions in the space over certain amounts of time. But the thing we observed, if you give these people questionnaires and you ask them really to explain the causal structure of the system, one thing that stood out is that those visitors who were really actively engaging in this environment had a much better understanding and recollection and also subjective experience than those that were passive. And that then set us on a whole path of discovery on how we could explain that. Why would an active user of such a space have a more positive subjective experience and also a better recollection of what the hell happened? Okay? So what we learned was that active brains learn better than passive brains, which means forget the billiard ball zombie model. It's not explaining, apparently, what we measured here. Okay? And then, as a follow-up, we actually took this behavioral observation and translated this into very concrete technologies that we use in neurorehabilitation, in education, in this case, education of the Holocaust and Nazi crimes, and also in big data processing and STEM training in school. So we took this core observation in 2002 and thought, okay, this is going to give us traction in the real world, and we generalized it. It actually works, okay? But we still don't know why it works. So that's what we're going to try to understand now. And that's a lot to do with volition, it turns out. So let's focus on this adaptive layer. And in particular, let's focus on the hippocampus, this blue banana that sits here, which is a structure that is centrally relevant for memory. Right? So how do we know that? Well, of the many different forms of memory, we have procedural and non-declarative memory. That means memories you cannot declare, you cannot consciously speak about. We have procedural memory that allows you to perform tasks, physical tasks, to move around in the world. But then we also have declarative memories, memories we can really speak about. Like the one you're going to express tomorrow. I was at this talk and it was awful. Okay, you can declare it, even though you're wrong, but okay. Now, going back to Henry Molaison, you might have heard his name, or HM, the famous patient HM, was a severe epilepsy patient. As a sort of a measure of last resort, this structure, the hippocampus, was dissected out, although in the post-mortem it became clear that it was not fully removed. It's okay, that is just a complication we're not going to think about right now. But what happened after this surgery, he had lost all his abilities to form memories. Right? So with that, people started to become very obsessed with understanding how then this specific structure could account for the formation of memory. So okay, this is another view again on the hippocampus, which is, you can think about the hippocampus, if you take the cortex, which is about the size of a pizza, but a lot thinner though, if you just roll it out, at the end of the sheet sits the hippocampus, right? So it receives the information coming through this cortical sheet, and then it loops it back into that cortical sheet. It's the loop at the end of the sheet of the cortex, okay? And it's all folded up to fit it inside your skull. Now, if you make a cross-section through the hippocampus, this is a drawing by Ramon y Cajal from the late 19th century, you will see that there's a very distinct set of structures you can identify on morphological grounds that are also connected really as a loop. So it's the loop at the end of the cortex. And if you measure in this loop, let's say we go to this area called CA1, cornus ammonis 1, you will see something very particular. So this is from Kate Jeffrey's lab. We have a rat going around. We're measuring here in CA1 with an electrode. The rat runs into space, and every dot here indicates when this neuron is active. And then what you will see with time, and in gray we see the trajectory of the rat, we see that this neuron has a real preference for a location. That's also what I call place cells, right? Discovered by John O'Keefe. And John O'Keefe got the Nobel Prize for this in 2014, together with Maybrit and Edward Moser, which we're going to talk about a little bit later, right? So these neurons are interpreted as place cells. And it also led then to this whole idea that maybe the hippocampus is like the brain's GPS, helping you to navigate in the world, right? So we built many models of this. Here we apply them on robots. So here you see how we can develop such a place cell on a robot based on models that really try to capture most of the anatomy, the physiology of the system that we know. So with time, we've built different models of this whole hippocampal loop, tested it in real-time models, offline models, and what have you. So we did all these different stages of the hippocampus, we modeled that. But then, so about 12 years ago, this whole idea that this was just essentially a GPS system became questioned. Right? And also the way we could map this to episodic memory became a bit of a riddle because what people observed, this is in the Moser lab in Trondheim in Norway. If you put a rat in an environment that is rectangular and you slowly morph it, you slowly change this room into a circular room, like a circus, but we do it slowly. Right? As you measure from this area, you see something that would suggest that it's not really only a GPS. So what they did, they measured many neurons in this hippocampal, in this case in dentate gyrus. Like many neurons, so now you have a vector of responses, on, off, over time. Okay? So you can say, okay, this space I can re-describe now with this whole set, this whole vector of responses that I measured. And then what they plot here is just a correlation across these vectors as you slowly change the environment. And you see how the correlation is slowly diminishing, very gradually. Right? And that was a riddle at the time because the idea was, well, this system should represent space as an attractor. So it's either space A or it is space B. It cannot be space A and B mixed. Right? But what they observed, that there's some sort of mixing going on that cannot be explained. So, so that's the work of Maybrit and Edward Moser. And they worked a lot on these kinds of the spatial properties of the hippocampus and the so-called grid cells that represent space in a somewhat different way in the entorhinal cortex. So we had theory, we had lots of robot experiments, and we had shown that, wait, did I lose my slide now? No, I didn't. Okay, let's jump forward here. So, in the DEC theories, if I expand this a little bit, forget the details, not important. This is a way to depict the basic ideas of how the working memory systems and the decision-making in this theory work. Okay? But it made a very fundamental assumption, and that is that optimal decision-making is dependent on conjunctive representations. What does this mean? It means something really simple, that your representational primitive is not unimodal, but your representational primitive integrates sensory states and action states. And if you are willing to make that assumption, you can be optimal in your decision-making, Bayesian optimal. Okay? It was a strong assumption we made, that we could explain some things of behavior, making that assumption. But it's still required justification. Okay? So now, our friend John Listman, who unfortunately passed away 2 years ago, John had this fantastic insight. But okay, you make this assumption about conjunctive representations, and maybe that's exactly the missing link to understand the rate remapping in the hippocampus. Okay? So why would that be? Well, what John understood is, look, the basic idea was the hippocampus is dominated by information about space. Okay? So that would mean if I run around in this room, the XY positions I visit remain largely the same, even when the room becomes slowly circular. Overall, I visit the same XY positions, right? So it should still, in that sense, if my representation is only about space, the difference should not be too big. It's still a GPS, right? But what John realized is, look, if you really look anatomically at the inputs to this whole memory system, they don't only come from spatial encoders, so neurons that encode location, but also they come from neurons here in the lateral entorhinal cortex, as it's called, that are very sensitive to what the world looks like and smells like and sounds like. They're very much dominated by sensation. Okay? So John proposed, well, maybe we can explain this strange rate remapping that is such a conundrum now, that is questioning this fundamental idea of the hippocampus as a GPS, by looking at how these two sources of information how sensation and action gets mixed in this system. So that's what we did. We took all the anatomy we knew and the physiology, built a model from that. And what we showed is that you can exactly explain this degradation of this population vector, this correlation, if you assume that the mixing of space and perception is about 30-70, right? So 30% of information is action and 70% is sensory. If you make that assumption, you can exactly account for these rate remapping effects. Okay? And then actually the Mosers went back in the lab, they lesioned this sensory pathway, and they showed that this whole rate remapping effect largely diminished. Okay, so confirming this model. So what this essentially tells us, as a first step, right, this memory system is not only dominated by positions in space, it's highly multimodal, and it's actually forming these conjunctive representations. It is merging space and sensation together. So if one neuron fires in this area, it tells you multiple things, not only one thing. So it's like action. If you think about a memory as an attractor that links different items together, action is sort of modulating the depth of this attractor, right? How strong this integration can be. So then we tested this out in a more systematic way with human volunteers that had to navigate a virtual environment. You have to go to a red box, you get a picture, an image, and then afterwards we ask you to remember whether you've seen something or not, and at what position you saw it. Okay? What we did in this case, we had people perform this task under two conditions. One condition where they had voluntary control. So we were thinking about, okay, how does the voluntary control of action with this modulation of memory affect now this recollection? Or they were on somebody else's trajectory, called yoked control. Right? What we observed there, just in memory performance, that there is a significant difference in both the quality of recollection, like how many hits you have in recollection, and your declared confidence. Volition seems to amplify both the quality of your recollection and the confidence that you express with it. Right? So now we have a performance measure. So we at first on theoretical grounds said, okay, action is a modulator of memory, right? And now we show in a more systematic way on performance grounds that it really has impact on the quality of recollection and also the confidence that people express with that. But then how is this actually done in the system itself? So for that we have a collaboration with the epilepsy unit of a hospital in Barcelona, Hospital Del Mar, where we could now use exactly the same paradigm on epilepsy patients that are implanted with depth electrodes. Okay? So now we could look, and since epilepsy often emerges in the temporal lobe, we have electrodes that are touching these memory structures of the hippocampus. So now we can run the same paradigm on humans who have electrodes in their brains. And they navigate in the space now, the first task. So they run down these alleyways, they go to a room, they're asked to go to the red ball. Once they're at the red ball, we show a picture at a certain location, right? So that afterwards, we can look at how the rooms and the images are combined in their memory. We could present them now the same image in a different room and see then how the presence of that room modulates the quality of the recall, right? So that's basically how this works, right? So now in the recall, you bring somebody to a room, maybe they've been there, maybe they've not been there, and you present them again with an item. So across all these electrodes that we have in these people's brains, we now want to extract some measure, some metric that tells us something about the quality of the recollection at the level of the neural response. And so what we do there is called reinstatement analysis, which actually is something rather simple. Okay? So what we do, you take your time series from every contact. You have about 200 contacts in the brain of every patient. Okay? So that gives you a time series of the local volume response, what's called the local field potential. That's how many neurons together are responding in that situation. Then you put that through a fast Fourier transform, so you get a power spectrum. Now you know what kind of oscillators are describing this time series well. So now you have a pattern of these oscillatory responses, or this power spectrum, that you average over a certain time window. Okay, so basically what you're saying is, I can describe the state of this brain as the average power across many oscillators. Right? So you can think about a choir. Right? You have the choir, they're singing. So if you want, every measurement point is like one voice. Right? And the voice will change over time. We extract the power spectrum. We get the frequencies. And for the whole choir, you can now make an average frequency distribution. So, okay, this is the state of the choir for these 500 milliseconds. Okay, this is basically what we're trying to do now. And then the analysis, all it does is say, okay, what's the similarity between these power spectrum profiles, these frequency profiles, as you encode information when you see it for the first time, and we have to retrieve it. Is there any difference between these two? Okay? So, and we found something that is rather astonishing. It's just published now in Nature Communication. So if you look at a picture in the same room or in a different room, right, you see that the similarity, so here we just look at the similarity of the choir, pre and post. Right? Is the song the same or different? You see that there's a certain similarity. So the frequencies used along this whole time window from 0 to 3 seconds in the encoding phase, right, are repeated in a very short period of time when you have to retrieve it. So the choir is playing back its song, but then compressed. Okay? If you are in a different room, you see that this doesn't happen. And if you look at the difference between the two, you see that there's a very distinct window where the pattern of frequencies is very specifically repeated, but it's shifted in time. So the choir sings the same song. It just does it earlier when it has to recall the song. Okay? And this is in the hippocampus. This is the structure that we looked at earlier. If you now look at the cortical structures that are interacting with this hippocampal area, you see something that's exactly the opposite. There you see a very strong effects when you see the same item. Only the picture matters. For these cortical neurons, they don't care at all about the room. But they start to sing the same song when you see the same picture. Okay? So what we showed here, so this is now a projection of this data. So this is all the data we have over all the contacts in the different frequency windows that we look at. And this is roughly what you get. Right? So basically this means hippocampal structures respond very early, repeating their song, and with that they trigger the response in the cortex that follows later. And this is distributed in a very specific way in these different frequency bands. Okay? But this also tells you something else, right? The language of the brain is much more like like music than just rates. It's not just rates that run over a wire, right? It's really complicated patterns of frequencies with very distinct phase relationships and so on. So that means now we understand how the brain encodes this information in this medial temporal lobe structure, right? And we know that the hippocampus is like providing a scaffold for recollection, and then the cortex fills in that scaffold with the details. Okay? And indeed, we show those in this paper, if you're interested in that it depends on distinct synchronization in this frequency band, that hippocampus and cortex are talking to each other in this very narrow frequency band to get this coordination done. So but this is what it means, right? So you have hippocampus, it sets up a context for the recollection, and then the cortex fills that in with item information. But earlier I had said that action is modulating this, right? So this is now the next thing that we have to nail. How does action or volition then perform this modulatory task? So this is work we have just completed now. There are two aspects to this. So here we have first a more macroscopic view on this, okay? So here we have the patient. They run around in the maze. As you can see here, we have the traces of the local field potentials in different areas. Here you look at the correlations or the effective connectivity between these nodes. Our first question was, okay, if I now compare trials where the patient or the subject is freely acting and making their own decisions with those where you have yoked control, you have no freedom, you're told what to do, what does that mean for the information architecture that we can identify across all these electrodes? So basically what we did, we calculated phi, or an integrated information measure, conditional entropy based, where we just looked at all these nodes and we said, okay, if I know the time series of one node, right, how much information does this give me about any other node? Right? So it's like a measure of the dependence between the different nodes. It's a first assessment of, does volition matter for a brain? And what you see, so in this case, volition is red and passive is green. This is time in milliseconds in a single trial. I've just compared them. And what you see is that just in terms of these information measures, there's a highly dynamical progression, right? The information relationship changes very rapidly, which I think is surprising at this really broad scan. But also it's distinctly different between trials where the subject is active or passive. So this already would be a first suggestion that it matters whether you have volition or not in how information is processed by this architecture. So then we went one step further and said, okay, try to nail it. Let's see, can we now bring that down to this specific interaction between the hippocampal structures and cortex? So here we have the performance, again, of healthy controls in this task. Here we have the performance of our patients, where, okay, we have 13 patients. We have statistical significant effects for the confidence of recollection, not for the quality of recollection. The patients are just very good, on the average better than the control subjects. So we look, in that sense, more at the confidence of the quality of the recollection. And what you see here, if you now start to compare with the same analysis, again, we look at the similarity of the choir at encoding and retrieval, right? And the hotter the color, the higher the similarity. And again, here we have the volitional case, and this is the passive case. And you see that in the encoding phase, the volitional brain shows a much higher level of the similarity between encoding and retrieval than the brain that has no volition. Okay? And if you then also map this to the performance, which I'm going to do here, if we're now going to map this to the confidence which people can recollect items versus the items that they do not recollect well, we see a marked difference in this reinstatement value between these two conditions. That means we can now map the neural reinstatement response, the similarity in the response of the choir, really to the performance of the subject. Right? So that means we can now bring back, we can really now say, okay, we started in 2002, where we observed, okay, people who are active in a complex task have better recollection, and now we know this has everything to do with how their episodic memory systems of the hippocampus and the cortex together are encoding this information in these complex frequency patterns. Okay, so we've really now explained this memory performance in terms of the volition that is driving the memory. So volition matters. So we started out by saying, okay, we should point our telescopes to the brain, which we've done to some extent. We learned a few things. And we've been mapping this to different concrete interventions that we hope can also improve the human condition to some extent, because we have to, in the end, bring our science to bear on real problems. Right? It's nice to pander to your peers and to be the smartest guy in the room, or try to be, but that only gets you so far. Right? I think science also is about pragmatics. It's about changing the human condition. It's changing the universe. That's what science is about, right? So otherwise you can go on TV and play any of these TV games, right? And be really good at that. So we need the science to improve the human condition. And what we can contribute to that now is that if at the heart of that science also stands an understanding of the human brain, we must find ways to return agency and volition to these brains, because that's when brains operate more effectively. So for me, if you look at the Sustainable Development Goals, these are all symptoms, in the end, of malfunctioning brains. Right? We're looking at malfunctioning brains because brains have limitations. And we know them. We just don't know how to overcome them yet. So how are we going to do that? let's jump forward a little bit. So I believe we have to really think about building a science and a technology that can support these sustainable development goals. At the heart of that stands very much the question, what it is to be human? Which again is partially reduced to our brains. And on the other hand, also to the social cultural environments in which we are embedded. And so we have been looking more specifically at the nodes in this network of health, education, and identity, as I mentioned earlier. We built interventions for that, so let me give you some simple, just some quick examples where we are. As I said earlier, scientific theories are about explaining, predicting, and controlling. If you're not loading well in any of those things, it's an opinion. So how are we doing with control? Well, stroke is our concrete test case for health. There are over 40 million chronic stroke patients worldwide. The lifetime risk is about 18%, and your life expectancy afterwards is about 4.5 years, which is not a good situation, right? So we have to do something about that. So we built virtual reality training environments where we project the brain of the recovering patient back into a task space that we manipulate. And we manipulate this task space to help this brain to find alternative solutions in a more holistic, goal-oriented, volitional perspective. Okay, this has been the driving consideration. This paper just came out now in Journal of Neurophysiology, where we show, this is a group of 217 patients that are treated starting at either 3 weeks post-stroke to 3 years post-stroke. They all got an intervention only of 3 weeks, 20 minutes, 3 times a week. And we have significant impact at all stages post-stroke, okay? So these core ideas we had, empowering the volitional brain, translate to real things you can do in the real world, in this case in the clinic. So now one of our challenges is to scale this. We want to bring this to as many patients as possible. So far we treated over 2,000 patients. We deliver dozens of interventions every day. By now we have delivered over 46,000 sessions, over 5,600 hours of therapy, only with these virtual reality interventions, right? No humans needed. Identity, another core issue that also brings us back to our history. I think one reason why we see our society fragmenting to the extent it is happening is also we have lost a sense of common objectives and a common path through time. So we have to reflect more on our common history. And for that, I think it's essential that we also educate each other and our citizens better about where we're coming from. And certainly for Europe, an important part of the history is Holocaust and Nazi crimes. There are about 42,000 sites across Europe that were implicated in the Holocaust in some way. And most of them will look like this. Nothing there, nothing to be seen. We're the Nazis from outer space. In 1946, they all disappeared again. Okay? By losing that history, right, we happily run after the next propagandist again. Okay? And we see populism rising. But it's not the fault of the people who run after these populists. It's the fault of us not educating each other sufficiently. So for that, we built virtual reality and augmented reality applications that, again, allow people to see what was there and to discover the history of these sites. So this is in Falstad in Norway, for instance, where people use tablets to run around. They can see all the barracks that were standing there and the barbed wire and so on, and discover the history through diaries, pictures, sketches, and so on, interviews. This installation we have in the Dutch National Holocaust Museum. So in this case, you can navigate the site of Bergen-Belsen, a Nazi concentration camp close to Hanover. But again, you see, we use the active brain to optimize the learning. It's the same principle. And it turns out to be highly effective. But these are very concrete interventions we can now scale because we have some idea about principles of organization of experience and memory, right? So with that, we're also back at why this happened 75 years ago. And we owe it also to these men to not drop that legacy, right? Because we're too complacent just liking Instagram pictures, okay? So this is our challenge, understand the brain, but with that to also create the virtuous life, right? A life that's worth living. And that's not the life of only resource accumulation, right? Don't forget, for the Greeks, eudaimonia was about virtue. So I believe we have to rethink our relation to technology in terms of augmentation. So with that, we are back also to the post-war period of one of our Bush, Science Endless Frontier, and the augmenting project of Engelbart. I think we have not given this enough credit. We have to rethink the roots of our technology much more in terms of these initiatives that have fallen by the wayside. Yeah? So build a new science of the Sustainable Development Goals in terms of augmenting human fallibility, the human brain. But then we should also not get distracted, right? So on the one hand, everything is easy if the person doesn't have to do it, right? It's like I said earlier, a scientific theory has to explain, predict, and control. It's not just a bag of words. It has to get done, right? To have an opinion is easy. To get it done is hard. And we should be sensitive to that. Getting it done is hard. Don't believe the hype. However rich people are, it doesn't give them wisdom. They just have a lot of money, right? Doesn't, okay? So let's not jump on that train. And also in that sense, I think we should be really careful how the current critics of the tech industry are in some sense also condoned and acknowledged by the tech industry. They're part of that gravy train. They're not really criticizing it, okay? So I think we should be a bit more critical in how we interpret what these people say. The real world is more interesting than science fiction, so we don't need Asimov to tell us how to regulate our relationship to technology. And I think maybe one of our biggest problems that we have to overcome is we have to find a much more unified view on how we advance our science of the human condition across disciplines. We have not succeeded in doing that. And this is really a massive obstacle right now because people just don't even understand what they're saying to each other, okay? I think we made some progress on that. We call our project Sapiens 5, the next phase of humanity, right? What's it going to be? I believe it's going to be about augmenting the human brain, and we start to make some small steps in that direction. Thank you very much.